Okay, let's look at the last one if you've been watching these in order. So there's two parts to this one. We have part A and part B. Overall, what it says is a street light is 15 feet above the sidewalk. So that's given us a measurement. Jonathan, who is 7 feet tall, very tall, walks away from the light at a rate of 5 feet per second. So let's draw our lamp post. We'll make it all pretty. There's our light. Yay. Okay. Beautiful lamp, I know. So our lamp post is there. Jonathan, this makes a triangle with the ground. Jonathan, here's his little head and arms and feet. Yes, I know, he's great. So is there. We know that Jonathan is 7 feet tall. We also know that our street light is 15 feet above. And we know that Jonathan is walking away, so this little guy is walking away at a rate of 5. So we don't have any variables yet, so we don't really know what that's going to be. We'll probably use x and y because that's easiest. So what we want to look at is if we have two unknowns down here. We have the distance between the light and Jonathan, and then we have Jonathan's shadow. Because part A says determine a function, so we're figuring out an equation relating the length of Jonathan's shadow, so here's the green, that's his shadow, to the distance from the base of the street light. So that's there. So we have, let's call this x and this y. We have two unknowns, and those are the two that we're relating, which is why we're giving them variables. So if we write this up, we can see that there are two triangles. We can see that there is a bigger triangle. So right here we have a bigger triangle. And here we have a smaller triangle. So we're going to use this idea of comparing sides. So we have in the smaller triangle, we would have the side y, which is right here. And let's compare that to 7. So we're going to have ratios. Then in the larger triangle, we have this huge side, which is actually x plus y, over, if we compare it to the side that it is related to, is 15. So to get this out of fractions like this, let's cross multiply since there's an equals in the middle. We can have 15 times y equals 7x plus 7y. There's our equation, but let's get all the x's and y's on the same side. So we can subtract 7y and we get 8y equals 7x. Then we divide both sides by 8, so we'll just get y equals 7 over 8x. And there's our equation that relates his shadow and the distance from the light pole. That's probably the hardest part about this, is figuring out that equation. Because the second part of this says determine the rate at which Jonathan's shadow, let's go back down, come on, the rate at which Jonathan's shadow, so the shadow has to do with y. We are determining y, so we need to figure out dy dt is lengthening at the moment when he is 20 feet, so x equals 20. And if you look back up at the very original problem, you have to be careful because sometimes this information is all over the place. We have a rate. Goodness gracious, this darn computer. We have a rate here, a rate of 5 feet per second, and that is him walking away. So the rate at the bottom that x is changing, so dx dt is 5. So we're going to use our equation that we found. We're going to take the derivative, and we're going to use this information to find what they're asking us for. So our equation that we wrote is y equals 7/8 x. Y equals 7/8 x. We need the derivative, so that's dy dx. 7/8 is just a number, so it's going to stay. And the derivative of x is dx. We are taking the derivative with respect to time because this is related rates. Focus. So, dx dt. Okay, so we need to find dy dt. And we need to plug in dx dt. So really, this rate, don't need x 20 feet from the pole. We really just need dx dt. This computer, dx dt. So dy dt is equal to 7/8 times 5, which is 35/8. And my measurement is feet per second. Feet per second. There we go. There's our answer.